Okay, so sorry, a little bit of technical stuff, but at least we have started. So yesterday we were talking about neural networks and deep learning. We couldn't really finish it off, so we will finish off our discussion on neural networks, and then we'll talk about deep learning a little bit, and then hopefully within 45 minutes or so, we'll move on to today's topic, which is unsupervised learning. So this is what we were doing yesterday. We said that we want to model, we want to develop a computer that looks sort of like a human brain, or at least works like a human brain does, or an animal's brain does. And we said what we do is we get a sequence of inputs here, and then we weight them somehow and pass it through a function. And if your inputs are high enough, you will activate your output. That was the plan. And then when we started with a single neuron, and then we went on to networks of neurons, or multiple levels of this. And we found out, and the main thing here is in neural networks is, so we have an interconnection between inputs, hidden layers, how many you want, and then the output. And the main challenge then is, how do you figure out the weights that connect the different units together? Okay, that's the thing here. And yesterday we saw that the way to do it is something called gradient descent. Right? And then we generalize gradient descent to the case where we have multi-layer networks. And this is sort of where we ended last time, and I was trying to show you how we do this. And the main thing is so essentially we want to change the weights in proportion to the errors that we are seeing. If the errors are higher, then you have to change higher or lower, depending upon the magnitude of the error. That is this tk minus ok. That's how we change our weight. Right? And in addition, we also look at the gradient that looks at, if I change the input, what is the rate at which it will change the output? So we take that into account. And the other thing we saw last time was, if we have a multi-layer thing, we only know the errors at the output nodes. We don't know what the errors are at the nodes in the middle. So what we do is we do something called backpropagation. We take the errors at the output and sort of move them back step by step to its every stage. And the way we do it is we weigh it by their contribution to the output. So we saw that last time. And what we will do is we'll take a look at a few more properties or other things that we need to worry about, and then we'll move on to deep learning. So one thing that we see is, when we are talking about this kinds of multi-layer neural networks, it's very non-linear now, right? Because this squashing function is non-linear. If you put your weights high enough so that you're operating in these ranges, so this is my squashing function, right? If you're somewhere here, for example, or somewhere here, your output is very non-linear. You make a tiny bit of change, and you'll have a lot of difference in the output, right? This is useful in the sense that it allows us to partition boundaries which are not linearly separable. That helps us. But then what it also does is it sometimes can make us get stuck in local minima. So for example, in a real life scenario, this might be your error surface. Right? It may have one global minima, but many local minima and so on. And here, what we are doing is, if we don't know exactly which way we need to go, we may get stuck in places like this. Right? So what we do then in that case is, we do things like, we add a momentum factor. Right? See, imagine what is happening. Why did I say we can get stuck in that local minima? Because the initial weight that we are choosing is random. Right? We start with an initial random choice of weights. If I go back to the figure here, if you're lucky, maybe you have chosen your random weight to start somewhere here. In that case, your gradient that you will calculate will really be in the direction of the real gradient that you want to go. But let's say you are unlucky and you picked up here. You started off here. Then the gradient that you will calculate will be towards this valley. And then at some point you will reach this valley and you'll get stuck there. We don't want that to happen, hopefully. So one way of doing that is to add this factor called momentum. In this case, what is happening, let's see, right? Previously, what did we do? This was our factor, right? Wi is changed by delta Wij, where delta Wij is this factor. So now what I do is, so this was the previous factor. This is the previous case, right? This is the normal case. This is how I calculate my change in the weight value. Now I add this function. What this says is, at the nth iteration, I add some component which is based on the weight of the previous component, previous iteration. What this does is, it's sort of momentum. If you are moving with a high velocity, you tend to move in that direction, right? So previously, if your weights were high, you would continue to move. So as a result, what would happen is, hopefully, you will not get stuck in this local minimum. So let's say you are here, you are descending like this, right? You're descending like this. You are descending quite sharply, and you are here. If your momentum is high, hopefully it will push you through the valley. That's intuitively what's going to happen. Right? If you keep your you descend, if you're only incrementing a little bit, you'll get stuck here. But if I add a momentum, that's so previously you descended quite sharp. Now that momentum will carry you through the valley, and you'll reach the top, or hopefully cross the top part of the thing, and then you can proceed along. There's no guarantee of that will happen, but hopefully that happens. Hi. And the whole thing to remember about neural networks is that the training can take a lot of time, especially if you have many hidden layers or many hidden nodes. Right? So training can take time, but using the network after the training is done is usually very fast. So I'll just walk you through this backpropagation thing that we learned very quickly using an example to see what happens. So in this example, what we have is, I want to make the machine recognize the voice of a person. Right? So there are two people, let's say Steve and David, and they're both saying hello, and I record it. I recorded them saying hello, and what I do is, I will train the machine so that if, again, I play back a hello, it will tell me whether David said it or Steve said it. It will recognize the voice of the person. Right? So I have to have two machines, or two neural nets. One will be trained to David's voice, one will be trained to Steve's voice. Okay? So that's what I'm doing. And what we have is, so when I say hello, what you do is you record my voice, and you can do a spectral analysis on this, and see what are the frequency components that are present. So all the way from 0 Hertz, usually human voice doesn't go very high, a few kilohertz is okay. But these are the frequency components. So you see most of it is the lower frequencies and some at the higher frequencies and so on. So what I do is I have a thing like this. So I have divided into 60 bins. So I have 60 inputs, 60 frequencies, 60 different frequency parts. So my input layer consists of 60 things. And at the hidden side, I have 1, 2, 3, 4, 5, 6 nodes, 6 hidden nodes, and it's one layer. And at the output, I just have 2. Yes, no. Is it David? Not David. Another machine will be there, or another network will be there, and that will say Steve, not Steve. Right? So I have these two. So I'm training both of them. If you look visually, there's a little bit, but they're more or less the same shape, right? As a human, maybe difficult to discern what's going on, just by visually. So this is what happens. Initially, we just select some random weights. I think it was 0.1 or 0.01, something, I don't know. But anyway, you start off some random weights, and you figure out what will be the error. With those random weights that I started out, the output here is 0.43, 0.26, 0.73, 0.55. That's what the output came out. That's not good enough, right? I want 0, 1, 0, 1, or 1, 0, 1, 0, whatever it is. So what I do is now I see, okay, what is the error? Here I wanted 0. Here I wanted 1. Here I wanted 1, here I wanted 0. So this is my error, t minus o. T minus o factor is this. And now what I'll do is I'll propagate it back. Oops, I'm going in the wrong direction. So I will propagate this error back. And I'll update the weights of all of these branches that are coming in. Right? I'll update that. And once these have been updated, I will update these weights by backpropagation. First step, update these, then we update these. And then we keep doing this many, many times. And hopefully at some point this comes out to be 0.1 and 0.99 and so on. So close to 1, this is good enough. So that's the idea. And in the interest of time, just to move quickly through what we have been doing. So what about the convergence, right? So what can happen is, depending upon where you are, where you start off with, and what kind of surface you're dealing with, you may get stuck in the global minimum. So what we have seen is we can add momentum to it. And then hopefully that takes us out. Another option is, so I started with some initial vector. Some initial set of weights, right? And what I can do is, I can train this. And I see what is my final error value. So that's one, right? So now what I do is, I will start with a different set of initial values. Again, training. Do the same thing. Repeat the same process 2 times with different starting points. And then I can compare. Is the error at the end the same? If they are the same, then I have some confidence that I have reached the global minimum. If they are not the same, then one is stuck at a local minima and another is stuck at a global, or maybe it's a different local minima. So you can do this a few times with different starting points and see whichever gives you the lowest one. So that gives you some idea, some confidence that you are not stuck in a local minima. That's another option. And how do we start? And what kind of convergence should we have? So what we should do is, we should initialize the weights near 0. You shouldn't start off with weights of 0.95, whatever, right? Start off with some, you don't want to start with 0 either, then nothing goes through, right? Start off something so that you are still in the, so you have your squashing function like this. Squashing function as a slope parameter or whatever, right? So based on that, this part is roughly linear. Right? So you want to start off in a linear range somewhere. And there's a reason for that. What will happen is, if you keep your weights near 0, your initial networks that you're working with will be sort of linear. All the neurons that you have in your network will be operating in this range. Right? So you will be operating in, so what happens is, as you train, hopefully the weights will go up, and at some point you'll get the non-linear surfaces that you want. That will happen. But starting off with this, what helps us is, when do all these things come up? These are very, very non-linear places, right? They happen when you're operating here. I don't want to start off at a very, very non-linear place. There's more chances that I'll get stuck. So I start off with a linear region where I hopefully don't encounter this kind of phenomenon. So that's a rule of thumb. And what is the inductive bias here? When we were doing our conjunction-based find S or whatever algorithm 2 days back, the bias was that I'm restricting my hypothesis search to conjunctions, only ANDs, right? And then when we were doing decision trees, our bias was we prefer shorter trees. In this case, the problem with neural nets is, we don't really understand what's going on inside. We have chosen the weights, but what does it mean? I can tell you what it means for a single neuron, that's fine. But the complex interconnection that is there, that's very difficult, so we don't know. Right? But what you can think of this is, one thing is, one bias is that I am assuming that my concept that I'm trying to learn can be characterized by this W. My hypothesis is contained within this W. That's one. And the other thing is sort of the input data should be sort of smooth. That's another, because we are differentiating things now. The whole thing is based on differentiation. The gradient updates and so on. If you cannot differentiate that, then you cannot do anything, right? So that's one of the issues. But anyway. And finally, we can worry about overfitting. So what happens is, if you let your, if you want the error to be small, right? When we're trying to recognize Steve and David, I guess, right? We let it run, let it run, let it run, till it came to 0.99 and 0.01. What happens is, in a general case, if you let it go very, very fine, again the same thing, you're learning the specific training examples that you have learned, that you have been given. Can this generalize to something you have not seen? Usually we run into trouble. So what we say is, one thing is, we can set a threshold saying, okay, as long as the error falls below this, instead of getting exactly 1 and 0 at the output of Steve and David, let's say if you get to 0.9, I'm happy. That's good enough. You can set a threshold like that. But the problem is then, what is the threshold value? So usually what would happen is, the most common way is again that what we did yesterday. You have your training samples. You break it up into 2. And then you fit your model on one and test on this part. And as this one shows, as you keep repeating your that backpropagation algorithm, as you iterate more and more and more and more, of course you're learning that very, very fine, complex thing that surface that is there. So your error will go down. But at some point, for example, starting this point probably, you're tuning very, very specific to the examples you have seen. They only fit the examples you have seen. They're not general anymore. So on the test part, error will start increasing. So you want to stop somewhere here. But what also happens in real life is you may not observe such a nice smooth curve. It may even look something like this. And this is based on the training that you're working with. This is nothing, there's no scientific reason as such why this happened. It just so happened your samples were like that. So it can happen that the validation error set goes down, then it can start increasing. So if you had stopped here, wouldn't be right. So the idea is that even though at some point you see that the error has started increasing, don't stop yet. Keep those values here, whatever weights you had calculated here, keep it in your memory. But try going further. If you see this kind of pattern, then you know that, yeah, I'm overfitting. Then you come back and say, okay, this was my best position, I'll use this value. So when you're trying to fit your model, don't just stop here. Keep doing. Then you can come back and say, this was the best error. So if you stop here, then that's not the best performance you could have obtained. So you continue, at some point, hopefully you can stop here. Questions?
Sir.
Yeah.
In the speech recognition example, you took 2 different networks.
2 different networks.
So is there any specific reason you could
No. You could have had a network with 4 output nodes, for example. That's not just an example. So you could have had a thing which says, there'll be 4 output nodes. One will be Steve, one will be David, yes, no, whatever, right? Or you could have just 2 nodes. One will be Steve, yes, one will be Steve, no, or something. But then your inputs will be larger, you have to give both the inputs. Just by looking at, so you would give, it would have 60 plus 60, 120 inputs. There is no reason why they should be separate. You could have a single network to do the same classification.
There is no hidden layer here.
There is one hidden layer, this is the hidden layer. These are the inputs, these are the 60 input nodes. These are 6 hidden nodes, and there are 2 output nodes.
So this only works with the binary kind of classifying is basically binary classification.
So this is binary.
For continuous
So for example, what we did yesterday with the driving thing, that's sort of continuous. Right? I can go from straight all the way here.
But you have to define those.
Exactly. So in that case, what we say is between 0 to 2 degrees is one bend. 2 to 4 degrees is another bend. So you sort of take your continuous space and your.
So no way to get the continuous value direct.
So you could. So you could say that. Where did it go? Yeah. It's the way you want to interpret this. the output is a continuous number anyway. Right? So it could be, for example, there is something called a, do I have it here? Right, let's go. I think it's called an So what you are outputting is, so let's say I want this. So this is my neural network, right? Whatever layers. Let's say I give you an image. And let's say my job is, whatever it is, I will transform it to another image. Or I will pick this and I'll do some kind of transform. In this case, I have these pixels at the image, at the output. Each of these pixels will be one output node. And what will that output node give? Some real valued number. And that, if you're considering it's a black and white image, that real valued number will go to this pixel value. So now I'm not saying it's binary. It's some real number. And when you see this picture, that real number will sort of say how bright that particular pixel is.
You have to interpret that value.
You have to interpret that value. Right? So it's up to you. If you think that I want discrete, you go for discrete. Right? And the problem really is then in many cases, we want to make a decision on something. Even if I have a continuous variable, in this case, continuous makes sense. So you have to think in your problem what makes sense. If you want to make this thing, you could say that turn whatever 2.3 degrees. That could come out too. But do I really need it? If not, you can make it a discrete. You make bins and then do it. Yeah.
So what is the best way to divide the data set into training and testing?
So what is the best way, right?
Yes, sir.
So there is a rule of thumb which says that this should be like 80-20, 70-30. Somewhere in that range. You usually spend 70%, 80% of your data on training and keep some on test. There's no fixed answer that says this is the split.
In two different lives, sometimes we use cross validation and sometimes we directly split 80 or 20. So if you divide the data set in 80-20, it is not bias the training.
No, so you have to start with your initial assumption. Initial assumption says all the data that I have come from the same process, same general population. If that is the case, then I'm not in a problem. Because I tested on something that comes from the real population. It's not a biased sample anymore. And I have not used those samples for training. So I'm not cheating. Right? So this is statistically accepted way of splitting things. So if you say that I have the data, I split it into this, and this was strictly for training, this was strictly for testing, nobody will question it.
Sir, in that example, you use that vertical shift or one single vector to input to the neural network.
Right.
So then people reshape the data and then they feed that thing. Which is the best one? In terms of complexity you have to see or the reduction in the architecture?
It's the same essentially, right? Even if you have, so for example, I have this thing, right? What I will do is I will convert this matrix into a vector.
But that will increase the number of nodes.
Even, so the question is, what is your data? In my case, a data is a pixel. So that many data I have to give. So each pixel will represent a data point. The other option is you want to add these and give it one, but you will lose resolution there. Right? So you don't probably want it. If you have whatever data, each point is a data. So that will determine your input. You can't really help it.
In some cases like images, like in ImageNet competition where I've seen some papers where they reduce the dimension of the matrix.
You could.
And they don't consider the RGB channel also. They take a grey image, inside they.
So those are very, very specific things that is tuned to a particular problem. So, for example, when you do deep learning, there are some special architectures which are just for images. You give it to that voice thing, probably doesn't work. So what they're exploiting is that they understand what I'm trying to do. They know that I have an image, I have to recognize a face or an edge or whatever it is. Then they exploit that property to reduce it here. That same technique may not work for anything else. If you understand your problem very well, if you have spent 5 years on it, you may be able to come up with techniques that you can reduce the size of your inputs and still work okay. And if you can do that, go ahead, no problem.
Image is nothing but a matrix inside.
It's a matrix.
Right. So if, for example, if I have a string of numbers and if I reshape like a matrix, then on perception I can say it's an image, and if I fill that thing again, so does the actual image and it will have a in the output, does it will show the same thing?
It will show the same thing because what you are doing is, inside the network, you're training it in such a way so that when the output comes out and you flip them back again as a matrix, you will see the image you want to see.
Reconstruction kind of things are there.
Yeah. So whatever I want to see here, if I don't see, I give it a high error. Right? So let's say there is a face of somebody here. I want to see the same face here. If I don't see it, I give an error here. To that, but if this particular pixel is not matching in the face, I give a high error to that particular output. That does something inside, which I don't know what happens inside. But it will make sure that if there's a face, edge of the face there, you will see it.
In that graph, in the validation and training graph, maximum time I've seen the validation graph remain below to the training graph.
Yeah, it may remain below the thing. That depends on your data and your thing. Depends on what kind of data you have. It could be higher, it could be lower, it could be same. Ideally, it should be the same, right?
Ideally, it should
be the same. But then, if you've trained well, it should be the same. If you have trained not so well, hopefully it will be higher. And if you get lucky, maybe it's lower.
So if it is of a single network you are selecting, instead of going for 120 nodes, shall we stick to 60 with the 2 set of vectors and 1 output node? Because identification is a person yes or no. We can stick with 1 node in the output.
So
is this possible?
if you could, yeah, and then say if that value is less than 0.5, it's yes, you could do that too, that's fine.
So instead of 120, we can stick to 60
But
also.
120 is, so let's say all you care about is, you get a voice sample, you want to know if it is David's or not. In that case, yes, only one sample. So whether you give David's voice or Steve's voice, doesn't matter. It will just say yes or no. I train it on, so let's say I train it on my voice. In that case, it gives a close to 1. Now if I give your voice, hopefully it will give close to 0. In that sense, I can differentiate whether it was your voice or my voice. Right? If you really want to see it that way, you could have just 60 inputs and you always give my voice. Or in your case, you'll give your voice here. And the output is just 1 node. That also works. Nothing wrong with that. This is an illustration of this. Alright, so 35 minutes on. I'm going to take 5 extra minutes, okay? We started late today, so that's fine. So, history of deep learning, right? So, I don't think I want to talk about history today, maybe more of the technical part. But if you want to see this, the whole thing started in the mid-50s, and then we developed the perceptron. But at some point what happened is people figured out that the perceptron only does linear classifications. So it cannot do things like XOR. And some guys, Marv Minsky from MIT, he published a paper which showed this negative result, and that sort of stopped everybody else from working on it. Right? But in the 80s, the people said that again, only one neuron cannot do XOR, but if you stack 2 or 3 neurons, you can do XOR. It's okay. And then people started doing things and neural networks took off. But then at that time, in the late 80s, early 90s, the problem was computational power. Computers weren't that fancy at the time. And the other thing is, whatever data they had, mostly unlabeled. So if your data is unlabeled, you really can't train things. Right? So that was the problem. And then things happened in the late 2000s, and we have more powerful computers now, and we have GPUs and so on, which can do things in parallel and so on, so speed it up. And now we have a lot of data which is labeled. Another thing which happened is, now we also have algorithms that can make use of unlabeled data and still work very well. So now we have more and more interest in these things, which is coming up. Right? But one thing is, the architecture at the core is still the same as the neural networks that we have seen before. Right? And the reason neural networks are popular is that, they can approximate very, very nonlinear functions. This is something we have talked about yesterday. And if your problem is complex, you don't know what's going on, and you have lots of data, neural networks can approximate it. Give it time, it will learn. Right? And they are flexible. You give it a different problem, it will learn accordingly, and so on. So what is deep learning, right? If you ask different people, they will give you different answers. So as to what is deep learning, some people will say that deep learning means that it has more than 2 layers. It has many, many hidden layers. Right? They will say, okay, that's the deep learning. That's one definition. For others, the deep means that now you can make use of unlabeled data. So it's deep. And more general is that, the deep learning is essentially a set of algorithms that uses neural networks as an architecture. That's fine. The underlying architecture is a neural net of the kind that we have seen before. But then it has some ways of learning the features automatically and so on. It figures out things and so on. It's just a combination of both things. So there are many algorithms that have been developed from last 10, 15 years, and that have really changed the way in which we think about neural networks, and they form one of the core. And the other part of neural networks and deep learning is, now people have picked up specific problems like pattern image recognition, and they have developed very, very specific architectures that can solve those problems in a very, very efficient way. So 2 of the algorithms that we were talking about, we'll briefly talk about, are something called use of rectified linear units. So yesterday we saw linear units, right, where the input-output is just proportional to the input. There are no limits. Another unit was the squashing function that had limits on the upper and the lower values of it. And there's something called dropout. So we'll look at these 2 quickly. So let's look at the use of rectified linear units in neural nets. Right? So this is my squashing function. And this is my rectified linear unit. Rectified means nothing below 0. That's it. So if you're an electrical or electronics engineer, a rectifier is something. You give AC, it will give out DC, right? It will delete all the negative values. So if your input is below 0, your output is a 0, and then you increase linearly, unbounded. Now, this may not make sense in the human brain because the neurons in your brain cannot produce arbitrary amount of output. They have a limit, maximum value, right? But this is a computer. I don't care what value you output. Right? So let it go higher as well. Only the output layer should be limited by something. Inside the network, I don't care. But then there are some reasons why I would want to use this function over this function. And why would I want to use this? So empirically we have observed that these rectified linear units have better approximation. That means they learn better. They produce better outputs. Why? As with most of neural networks, we don't really know exactly why. But we have some vague idea about why it might be so. Right? Why rectified linear units may work better. It's an open question, but some idea of it. So let's see what happens. So when you take the squashing function, I deleted the squashing function. So if you take the squashing function and you take its derivative, if you look at what we are doing, in our backpropagation algorithm, we need this part, right? So we have, what is the value, how much is the difference in my output, t minus O, that's my error. And then I have to multiply it with the gradient, right? With how the input relates to the output in the neuron. So this is the gradient of the neuron, if you want to think about that. So my squashing function is like this. This is a straight line, sort of. What does the derivative, what does that function O1 minus O look like? Looks something like this. And that's the derivative. It has a reasonably high value, it has some non-zero value or high enough value at 0. But as you increase, the derivative becomes 0. As you decrease, the derivative becomes. So as a result, what happens is, in the backpropagation algorithm, we need this value. This value sort of updates my weights here. Right? Because my weights, the change in the weight here, delta Wi, that depends on delta. And delta is here, depends on this. So what happens is, if you're operating in this region, or in this region, or even, right, that will be very close to 0. So as a result, your delta values will be 0, close to, because this is 0. So what happens is, you will not be updating the weights very much. And as you go from the output all the way to the input, these will be very, very small. So your input weights wouldn't change much at all. So that's the main problem. But if you use this rectified linear thing, what is the derivative of that function? Below 0, it's 0, right? It's a straight line. It's a horizontal line. So the derivative is 0. I have a discontinuity at 0. I cannot have a derivative there. But after 0, it's a straight line like this. It's a rectifier. Whatever is the input is the output. So it's a line at 45 degrees. So the derivative is 1. Right? So it's 1. So what this says is, my derivative sort of stays constant. And I can propagate my errors back in. It prevents the problem where, because O into 1 minus O is very close to 0, so nothing changes. That's one of the reasons. And then again, with the most of neural nets and this kind of things are heuristic, right? Somebody woke up one morning and said, okay, let's use this. I don't think that's what happened, but you know. So if I use this function now, is that the only thing I can do? Why can't I do this? So this would be a rectified exponential unit. You could use that too. And people use it. And you could tomorrow, you can come up with your own function for it. And you can see if that works better on your problem. So this is one of the ways in which things have changed. And the other algorithm we'll quickly look at is dropout. And in the dropout, what happens again is, it's the problem of overfitting. That's the problem we are trying to solve here. So in neural nets, as we saw, if you iterate many times, your error will slowly go down to 0. But now, what has happened is, you have overfitted. You are learning very specific things to the examples you have seen as input. You are very closely connected to whatever the input or the training samples are. Now, it may not generalize to a new test sample which you have never seen before. Right? That's the overfitting problem. So how do I solve it? What dropout says, so there are many ways, right? We looked, well, I didn't talk about these things. So there are a couple of ways in which traditionally people have been fixing these things. One way traditionally people have fixed is, how do I choose the initial weights to start with? Right? So we were talking about the choice of initial weights at some point, right? One option of choosing the initial weights is, So let's say you have decided on your thing, how many hidden nodes you will have. Right? Let's say I'm going to have 5 or 6 hidden nodes. I will first calculate the weight, some initial guess of the weights. How? I will use something called an autoencoder. What an autoencoder is, so let's say I want a 3-bit autoencoder. So I will have 8 inputs. Alright, these are 8 inputs. And I will have 8 outputs. An autoencoder says, whatever I give at the input, I want to see the same at the output. If I give this 1, 0, 0, 0, 0, 0, I should see 1, 0, 0, 0, 0, whatever. And if I give 0, 1, right, so I have 8 possible values here. I give this or, you know, I want to see the same thing at the output. Make the neural net learn this. So I have 8 training samples now. 1, 2, 3, and then so on until the last one will be like this. I have 8 training samples. For each of those, I want to see the output correct. When you do that, you will get some set of weights. Use that as your initial weights in your network. In some cases, it helps, right? And so anyway, let's not spend more time on this. So let's talk about this dropout thing then. Right? So what dropout says is, see, in an actual neural net, what you have is your architecture looks something like this. Let's say. Let's make a simple neural net. This is my simple neural net. Currently, what I do in my backpropagation is, do I have it here? I don't have it here. So currently, you give me a training sample here. I look at the output. I look at the difference, t minus 0, minus 0, and then I update. I update the weights. When I do this updating of weights, I update every weight which is possible for all the branches here, for all the connections. I'm updating for all the connections. What dropout says is, don't. Randomly pick some. Maybe this guy. I will not update this guy's weight. I will do the iteration. I will update everybody's weight, but I will not update this guy. Or, essentially what I'm doing is, I'm not using this neuron anymore. So what happens then? So what is the intuition? Why would this work, right? So previously what happens is, whenever I do the iteration, I'm trying to change everybody so that the output looks what I want. Now I don't have this anymore. So one way of thinking is, instead of just changing and I'm asking these guys to learn something extra. Right? So this is what it is. It forces the decision function to collect more evidence from other neurons. That's one way to think about it, rather than just trying to fit to a particular phenomenon. Right, so hopefully, the decision functions are more robust to noise. So you don't overfit and so on. And lastly, when we say deep learning, it sometimes also refers to things people do at the architectural level. And this is fairly common or quite popular in the area of image processing, where, for example, we automatically want to learn or recognize faces. Right? Or we want to find there's a dog, or I don't know what this is, I think there's a cow in this picture. Right? I want to see that there's an animal in this picture. So in this case, what people do is they say, okay, what do we usually do in an image when we're trying to analyze an image? So what we do is, I want to find edges essentially. Right? And one way of finding edges is to do convolution between different places. So what they would do is, they would have some stages here which are just specific for convolution. And then you'd have a traditional neural net with squashing functions and whatever. But these are not very general. So if you're specifically in the area of image processing, let's say, and you're interested in one specific aspect of image processing, then you would develop your own specific thing. I don't need convolution here, for example, if I want to do autoencoding. I don't need it. So it's not very. But many of these things are now possible because we have more stronger. Okay. Even though I wanted to, I guess, but I can't do programming examples in this 6 days. But if you want code for doing neural nets and deep learning, you can go here to this GitHub and get all the code. So the code which is present here, and you want to know what each bit of code does, sort of a manual and so on, first download this, and this will tell you what you want to do with the code, or what the code does, so you can play with it. I'm going to upload this anyway today at some point. Can I change or still waiting? Alright, all pencils are down, so I can change. Alright, before we move on to today's thing, I just have one other thing. Oh, I mean, so this is day 4, and in the end, if you have looked at the slides, I just had this. I didn't have the problem itself. Right? So I put that in today, and what I want, the problem here really is, I have a Boolean function of 3 things. Let's say I have 3 variables, C, A, and G, and this is the Boolean function I want, C and A, or C bar and G, or some Boolean function. Sorry, I forgot to put the AND functions, but this is C and A bar and G bar. This is my Boolean function. I want you to make a decision tree out of it. So for example, you could start with one of these variables, test the value of C. If C is 1, then you do something. If C is 0, you do something. Right? What do you do? Maybe I test B, so there's no B. Maybe I test A now, or maybe I test G now. So you write this as a decision tree, and that is what it is really. So at the root, we are checking C. If C is 1, so from C I have a branch like that, right? C can be 0 or 1. If C is 1, then I check A. If A is 1, then the classification is yes, or you output a 1 essentially. And if A is 0, then you need to check G. So so the way you could do it is you just write the truth table corresponding to this, and then you can just figure it out. Not very complicated. All right. So this brings us to the last part of this whole week-long thing, or 6-day thing. So whatever we have talked about so far has focused mainly on supervised learning. So for the next 2 hours or so, let's spend some time talking about unsupervised learning and techniques that we commonly use there. So this is the thing. We'll just talk a little bit about unsupervised learning. We have taken many examples on day 3 and even some on day 2. So distinguish between unsupervised and supervised. And then we'll look at 2 specific things that are commonly used here. Okay? One is clustering, the other is principal component analysis. Okay? So we know why we need, so some of the things about supervised learning is you need labels. Right? Somebody is teaching you or giving you labels. If this is the input, this is the output, right? So you need expert knowledge. If you're trying to identify tumors, you need a doctor. Right? If you're trying to say whether this power grid data looks correct or not, you need an electrical engineer, well, in India that's see in the US, everything is electrical engineering. Electronics, telecommunication, powers, everything is electrical engineering. Sorry, I just say electrical engineering, that's fine. But if you're looking at, so you need a power person to tell you whether the data looks right or not from the generator, right? So. And sometimes this labeling and so on can be expensive. And whatever you've learned for one class of data, labeled data, doesn't necessarily work for something else. Right? So what unsupervised does is it allows you to generalize things. Right? So the problem in a typical example in unsupervised learning would be maybe you have this kind of data. This data says there are 3 different classes of things. Right? Could be anything. Maybe these are children, these are adults, these are old people, whatever it is. I have labeled them as 3 different groups. But the data that you see is something like this. They're all X's. You just have data. You don't know who belongs to which group or is there a similarity between any of 2 of them. You just have something that looks like this. Then it's your job to say, okay, this looks like one group of things, which is very different from this group of things. And that's the job of unsupervised learning. How can I say that this is different and that is different? This is, visually you think, oh, this is quite far away. And that's sort of what we use. We use some kind of a difference or distance metric to say whether you're close or you're not close. All right. So let's start with the first way of figuring out who belongs in a particular group. And how do we group things together? And clustering. A very powerful technique for these things. So what it does is it deals with finding a structure in a group of unlabeled data. So my data doesn't have any labels. I don't know what is what. But I want to find some structure. I would say these look similar, they don't. And if you want to define what a cluster is, it's a collection of objects which are similar between them. And they're different from everybody else. Within the cluster, things are sort of the same, but from somebody from another cluster, hopefully they're very different. Right? So here I would group, okay, this is one cluster, this is one cluster. And why are these the same and these are not the same? One element here and one element here, they're not the same. I say, here the distances between 2 members is small, but here the distance is large. What is the distance? How do I calculate the distance? No answer. Depends on your problem and depends on you. You can define what distance you want to use. If it is just x and y and we are measuring, on a Euclidean plane, this could be the Euclidean distance. That's simple enough. But what happens if one is temperature and one is pressure? I don't know. So you have to somehow define your own distance in that case. There is no answer to it. And there are usually 2 types of clustering. Most common one is what I was talking about, distance-based clustering. I see how close you are to your own group members and how far you are from. And that is the most common way of doing clustering. And the other one is this conceptual clustering, which is based on ideas. Right? I think that these 2 objects that I've grouped together, they represent one concept or they do something. And the people in the other group or the elements in the other group, they do something else. So that defining concept is not very mathematical always, so we don't always use it. So the object essentially is to group things together, right? So what makes a good cluster? What's a good cluster? What are the things we want to look for when we are doing clustering? One thing is, there is absolutely no absolute best criteria which works for every clustering problem in the world. No. Your problem is very unique most of the time. So there's no absolute thing. So how we calculate the best is up to the user. You have to say, this is what I was looking for. So in some sense that becomes a bit challenging, right? How do I know if I don't know what the data is like? But you have some idea about what you are trying to do with the data. And based on that, you can come up with a criteria. So what are you trying to do with the data? Why are you trying to cluster it? Could be that you want to see representatives for groups. You want to have, okay, what does a child do? What does an adult do? How much money does a child spend? How much money does an adult spend? How much money does an elderly person spend? Right? So find representatives. So here we are interested in data reduction. I don't care about every individual thing. I just want to say, on an average, a child spends 5 rupees. Adult spends 20 rupees, something like that. Right? Or you want to say, okay, natural clusters. This is how things occur naturally. Most people, let's say, if I look at the population in Banaras, probably I would say, I don't know, this I'm just making up. Most people are vegetarians. Right? So that's a natural cluster. So vegetarians, non-vegetarians. It could be useful, finding useful groupings and suitable groupings. Very similar to this. It could also be used for doing anomaly detection. You said these are together, this is not together. This is one. Everybody is together except this one point. So that's an outlier. So you can classify, you could use clustering for that. If you don't belong to any cluster, any other cluster, or if your cluster size is much smaller than the other clusters, then you are an outlier. You could do that. And these are some of the applications that we have. Right? So for example, in marketing, in biology, for example, if you just give me plants, or pictures of plants or animals, or some of the height, length kind of thing, I will classify them. Cybersecurity is easy. Is it normal or abnormal? Insurance. When somebody files an insurance claim, how do you know this is a fake claim or a real claim? And so I could probably use clustering. I could see what a real claim looks like from my previous. Yeah, I could group all claims together and see if they all look the same. Hopefully, most of the claims are real. Right? Not everybody is sending in fake claims. So if a fake claim comes in, hopefully it will belong to a different cluster, and so on. So applications are there. And what we want are the usual things. They should be scalable. As my data increases, it shouldn't take too long. Right? It should scale well with the number of data samples I give. And I should be able to discover arbitrary clusters, different types of attributes. Right? It shouldn't just work for weight. No matter what attribute you give me, it should work. And hopefully it doesn't need any domain knowledge. That was one of the drawbacks when we said I don't want to use supervised learning. I don't need to know anything about medicine, but I will still tell, okay, this patient is sick and this person is not sick. They are two different people. I may not be able to say this is sick and this is not sick, but I should be able to say this is one group, this is another group. Which one is sick, I don't know maybe, but at least I can say that there are two different types of people. And deal with noise and outliers, and also the order in which you give the data, the way you're presenting the training samples, they shouldn't matter. When we were doing concept learning, the way we introduced the training data, that changed our specific and general boundaries. Right? So that shouldn't matter. Should be able to handle high dimensions of data and things like that. So in general, you can divide clustering into 4 groups. One is, these are the common ones, exclusive clustering. This says each member or each element in the data only belongs to one cluster, only one group. You're either an Indian or you're not an Indian. You cannot be an Indian and American at the same time. So that's exclusive clustering. And one of the common things, and we will look at this, is called, one way of doing this is called k-means clustering. And we will see what is k-means clustering. In some cases, we have overlapping clustering. In this case, a node can belong to 2 different clusters at the same time. And then you can have some kind of a weight. You say, with a weight of 0.3, it belongs to cluster 1. With a weight of 0.7, it belongs to cluster 7. So if I go back to the citizenship example, if you're an Indian, you can only be a citizen of India. Right? But if you're an American, America doesn't care. I guess you can't be a citizens of North Korea and Iran for America. But you can be an American and a Canadian and a British person at the same time, not a problem. How much American are you and how much Canadian are you? You decide. That's fine. Then there are hierarchical clustering, in which we have smaller clusters. They in turn belong to a bigger cluster. So as an example, I could say, I would group all the students in IIT-BHU who are in computer science. So computer science is a cluster. There's another cluster of electrical engineering. There are two different clusters, but they both belong to a bigger cluster, which is, let's say, School of or Faculty of Engineering or whatever you call it here. They in turn belong to a bigger cluster, which is IIT-BHU. They're all BHU students. Then engineering students. Computer science, electrical engineering, mechanical engineering. So we have hierarchical clusters that could be done. Well, one example of overlapping clustering is fuzzy C-means. And for hierarchical clustering, it's hierarchical clustering. There's no specific name for it. And then there is a probabilistic clustering where you say, with this probability you belong to this cluster and so on. So things like mixture of options. So what we will do is we will look at these two, which are the most common ones, hierarchical and exclusive clustering.
Are they same?
Hierarchical and exclusive? No, they are not the same.
Final classification
may not be the same. It will be different in general. So for example, with hierarchical clustering as an example, you can belong to computer science, and at the same time you also belong to engineering. You cannot do that with exclusive clustering. You only belong to one. So there is no concept of a bigger cluster that includes smaller clusters. Each cluster is on its own. Okay? Doesn't matter. Alright, so now let's come to K-means clustering. So here what I want to do is, I have been given some data. I want to make clusters or group them. Group what I think are similar looking data. How many groups? K groups. What should be K? You pick. You have to decide. So the first step is, you choose the K that you want. Now if I give you some data, you have never seen this, unlabeled data. Do you know that the K should be 2 or 3? How do you know how many groups are? So I have never been to BHU before. I don't know anything about IIT-BHU. I don't even know how many departments are here. And I have to group them. Let's say I want to group by departments or something. So I see students, I want to group them where they will be grouped based on their department. I don't know how many groups are there. So that's one challenge, of course. I don't know what is K. But the idea here is you try different values of K, starting with 2. K equals 1 is trivial. Everybody is in the group. You start with 2 and you cluster. Then do for 3. Then do for 4. Then you use some of your judgment, your own judgment, to see, okay, this looks more reasonable than that. If a cluster size of 3 looks more reasonable, then you say, okay, K should have been 3. I will keep the 3 one and I will throw away the other clusters. So nobody knows from before what is K. So you choose some K. Now what you will do is, you will initialize the cluster centers. So where is the center? So in a 2-dimensional plane, we are done with neural nets. I say these are the centers of the clusters, and maybe these are all the points that I have. I picked, so x's are given to me, all the x's, and I say, all right, I'm going to do K equals 2. So I arbitrarily pick 2 points to start with. I randomly pick 2 points because K is 2, and where should I put those points? I decide, I put it. Maybe I could put it even here if I'm unlucky. Doesn't matter. It's sensitive to the initial choice, but that's fine. So I pick 2.
So if we pick this point, so can it be of advantage to our problem?
Sometimes, sometimes not. Right? So that's one thing. Many people do pick the corners. Sometimes that helps, sometimes not. It really depends on what kind of data that is.
Maybe that it covers the whole.
This also covers the whole thing. So now what I will do is, It doesn't matter where I place it. So what I will do is, from this particular center point, I calculate the distance for everybody in the network, no matter where you are. I calculate the distance. Right. Same thing for the other guy. I calculate the distance. So another way of thinking, for every point, for every x, I know its distance to every cluster center. Right? Pick the one which is closest. This point, who are you closer to, this or this? In this example, you're closer here. So you belong to this cluster. And maybe a different color now. So you belong to this cluster. You belong to this cluster because you're closer to this guy than this guy. So you go to the closest thing that you have. I don't know if that was close enough, but anyway. So for each of the data points, I compute the cluster center that is closest to it using some distance measure. In this case, Euclidean distance. My life is easy. Right? And then I have the clusters now. Right? I have assigned every point to its closest cluster, the center point. And maybe this is what the clusters have become now. Right? This is iteration 1. Now what I do is, okay, I say you guys belong to cluster 1 now. You belong to cluster 2. What is the centroid of this cluster now? So how do I calculate the centroid? I will take the x coordinates of all of these guys. Take the average. I will take the y coordinates of all of these guys. Take the average. And maybe this is the new centroid. And same thing, this is the new centroid for this cluster. Now I repeat the same process. For every node in the network, calculate the distance to all the cluster centers. Has anything changed? Maybe what happens is in the boundary, now since the cluster has moved, maybe this is closer to this now as compared to that. So for some of the nodes, the classification may change now. For some, it may not change. So you keep doing this till no more changes are there in the assignment. So very simple. Questions?
Can we apply gap algorithm to know the number of clusters, optimum number of clusters?
To be honest, it will not work for everything else, every situation. Every situation. So any algorithm you come up with and say, okay, this gives me the optimal thing, maybe it will work for a certain scenario or a set of scenarios. It will not. It's very easy to come up with a scenario where it will not work. If you know what your data looks like, if you know your data is temperature and pressure, then you know my temperature doesn't vary more than 15 degrees to 45 degrees, let's say. Then you can figure out how many clusters should be.
How can I verify that it is optimal or not?
You cannot. You have to use your judgment. In this case, this is the 2 clusters, right? Now I will try with 3. K equals 3. And maybe that gives me some other thing. It gives me a cluster here. It gives me a cluster here. It gives me a cluster here. Now, it's my judgment. What is better? I could say, look, this guy is member of this cluster, but the distance is really too far from the center. I would prefer for you to be closer to your center. I said 3 is better.
Equal distribution of elements in the cluster.
That could be another thing. You want to have equal number of people in every cluster. Here, for example, maybe there are 8 to 7. And maybe here, whatever, 9, what is it? 10 and 7, right? So what should be here? 8. Yeah. 8, right? 8 and 8 is 16. Or I can't add things anymore. What is this? 9 plus 8 is what? 17.
17.
Is it 17?
Yes.
Alright, that's good then. So, in this case, the two clusters have roughly the same number of elements. Here there is one with very few. But maybe, as you pointed out, maybe I want clusters with equal number of nodes. So then I prefer this. But here, the average distance of a node from its cluster center is higher than here. If that is my criteria, then I go with this guy. So there is no fixed answer as to what we should be doing.
So what is the drawback of choosing the more number of clusters? Suppose I am choosing 2. Instead of 2, I am choosing 5. What is the difference?
So the difference really depends on your application. Why are you using this? So if your department, let's say I want to classify students. If there are only 2 departments, I shouldn't be using K5, right? If there are 10 departments, I shouldn't be using K2. So you cannot say that choosing more is bad, choosing less is bad. It's very, very specific to the problem you are doing. There is no one answer that says always prefer small or always. Sometimes small can have disadvantage in your case, sometimes big can have a disadvantage. No answer to that either.
Sir?
Yeah.
So there may be a possibility of singleton clusters also.
Could be. It can turn out.
Supposing K is equals to 2, I am getting a singleton, and K is equals to 3, I am not getting singleton. So which one is beneficial then?
Depends on you, what do you want? If I want to classify students, let's say, I want to select the best student, the very top students, the sort of good students, average, low. If that is my goal, usually at the very top of the class, maybe 1 or 2. At the bottom, I don't know, maybe 20%, 30%. In that case, I'm okay with a singleton cluster. Right? So you give me an example, I will come up with a counter example where singleton cluster is good. Right? So again, answer is it depends on what you're trying to do. Yeah, let's finish this guy and then we'll take a break today. What is happening? कुछ बता क्या आपने? नहीं. All right. Can I? Is there a message? I yeah, something. Thanks. मेरे computer में गया था. All right. So let's take an example of k-means clustering and see what happens. So let's say this is my data. No labels. Everything is a what is it? Is it a square or a circle? Let's go with a circle. Everything is a circle. Now I want to do clustering. We'll start with k equals 2. So let me go. So I'll start with k equals 2. And what you will see is it has randomly placed two circles. Randomly placed 2 center points. And then it will try to calculate the distance from everybody. And then assign them. And then repeat. So that's it. Which one was better? I don't know. You decide which one was better. And there's another way of, see when I was making the slides, I wasn't sure if it will play on the IIT computer or not. So I had another, this is no animation. So here again, so I start off with these things. So this is my initial data, let's say. And these are my initial clusters. And then I figure out where you're closest to. And then I will assign you. So for example, this one is now closer to this node. So it gets assigned to the different cluster. And then I will calculate the new centroid based on these 4 assignments and so on. So what are the issues with k-means clustering? You guys have been bringing up many questions along those lines, but let's look at some of the issues that are there. So one of the challenges is, how do I select the first cluster? I said do it randomly. So when you do it randomly, you will be doing k equals 2. If you start off with these two, you will get a different cluster. If you start off here maybe with these 2 points, maybe you will get a different cluster. So different starting points is determining the cluster. So that means it's not the real underlying phenomena which is determining, right? So there could be an issue on that sense. And data points in this case are assigned to only one cluster. So if you're computer science, you're computer science. What if I'm doing a dual major? Maybe I'm doing computer science plus, is there a dual major here? In some places you can do 2 things at the same time. Probably it takes a little longer. So, yeah, it's not always the case that I only belong to a single cluster. And this makes some implicit assumptions about the shapes of the cluster. Why? Because we are calculating sort of the distance. So you're making things closer together. So I'm not saying that the shape of the cluster could be like this. Usually you will not get something like that. When you see the final clusters in all of those, you will see them as closely bound groups like this. But in real life, a cluster could be like this, some arbitrary shape. It will usually not be able to pick that up. Right? And then the last one is you have to pick the number of clusters. And if I don't know what the data is all about, I don't know how many clusters are there. Right. And then one thing which we have been discussing a bit is how do we determine the correct number of clusters? There are some formal ways of doing it, and one thing is you have to have some kind of a measure of the quality of the clusters that you're coming up with. Right? You say, okay, this is the quality of my cluster, and then you have a metric that you define, and then you try different values of k till you get an optimal value. You say k equals 2, 3, 4, 5, 6, 7. What is the k, the q that I'm going? Right? And then again, what is the q? What is the quality? How do I calculate the quality? The answer is, again, depends on what kind of clusters you want. Again, there's no answer to that. One example where you want, let's say you want homogeneity or tightness or closeness. You only want to make clusters that are close together. In that case, it's easy. You can just look at the Euclidean distance. You sum up the distance of each member of a cluster from its center. Right? You have these groups, 2 groups. For each member of a group, I figure out what the distance is. And then I take the average. This is the number of elements in that group, number of nodes in that group. So this is the average distance in that group of the members of that group from the center. And I want to minimize this maybe. So this is the sum of the distances for all the groups. So I calculate what is the average distance for this group. I calculate what is the average distance for this group. I add it up. That's my final metric here. That should be as small as possible. Let me chalk that away, but anyway. But then, should it be Euclidean distance? Maybe, maybe not. Depends on your case. But the idea that I'm trying to give here is you could potentially define some kind of a quality metric and then try to minimize it. And then clustering can address some of the requirements that you have, but probably not all of them, right? That's one of the things. And dealing with a large number of dimensions. This was just 2 dimensions. If you have 55 dimensions, or 10,000 dimensions, as we were looking in the case of our supermarket example, things can become difficult. And really, those things are still okay. The biggest thing is this distance. How do I define the distance? That's sort of trial and error and your own judgment. So that's sort of it. And things like if you're comparing things with different units, distances and weights, how do I figure out the distance metric. So that becomes challenging. And how do I interpret this? What does it say? It just says they are close together. Beyond that, it doesn't really say much. So how do I interpret what this cluster means? That's it. So I think this is a good time for a break, and when we come back, we will do hierarchical clustering. So it's 9:58, so we'll come back at 10:08. No, your input is only 4. You don't have more than 4 inputs. Let me come down. Okay? You cannot increase inputs because it only has 4. If you could measure something in the you hear carbon dioxide, maybe nitrogen, etc. Then you would have 5 inputs. Right now you cannot.
As for the number of output, I have to increase number of input set is not
No, that doesn't, there's no relation. Okay. So that what in that case what will happen is because I have data from different people. If you are trying to say things like, okay, I have data from plant number 1 and plant number 2. I want to say this measurement is from plant 1 or from plant 2. So it's a different kind of problem. So then, if I want to say, is it your voice or my voice? I could just look at my voice input. Right? It's different from yours. Or I could give both your voice and my voice and use that as the data. Because the classification problem was different. I was trying to figure out the source. You are not doing source. Source is the same. So that's the thing.